All right, so the whole situation with chemistry is all about chemical reactions, right? So there are a few ways to determine if it's a chemical reaction or just a regular physical change. Okay, so like for example, a physical change would be like if water melted. I'm sorry, if ice melted. That's just changing water from its solid form to its liquid form. That's a physical change. We're going to talk about why that's a physical change and not a chemical change right now. So a chemical change or reaction involves the breaking and reforming of bonds. So in the last section, we talked about bonds being made and how those little sticks that go in between the atoms of a compound. So when those sticks break or form, that is that is a chemical reaction. Okay, so in that case, something new has been created. So you could take carbon dioxide and break the bonds between the carbon and the oxygen and form oxygen and carbon, two separate things. So two new things are formed from one new thing. Okay. Now there are some clues that visually or olfactory or auditory that you could kind of like pick up on to tell you, hey, that's probably a chemical change as opposed to a physical change. So some of those clues are burning, rotting, fermenting, rusting, tarnishing. A precipitate forms, which a precipitate is a solid that is produced when two liquids mix together. Or an unexpected color change. Sorry, I'm trying to get rid of that. There we go. An unexpected color change. Now, what we mean by unexpected color change? So, for example, let's say we have a cup of water and we put some green food coloring in it. Okay. You would expect that water to change green, right? That's an expected color change. And really, technically, that's not even a color change. That's just green food coloring kind of dispersing itself throughout the water. So really, that's not even actually a color change. But regardless, it's expected. Now, let's say we have 2 cups of clear liquid, and those 2 cups of clear liquid mix together. And when you mix them together, they make a yellow liquid. That would be an unexpected color change, right? Because you would expect if 2 liquids mix together, or sorry, 2 clear liquids mixed together, they would form a clear liquid. But since it formed a yellow liquid, that would be an unexpected color change. So what that means most likely is there was a chemical reaction. Okay. Next is a physical change. Now, a physical change, like we talked about with the water and ice, does not break or reform bonds. Okay, water, as hopefully we all know, is H2O. Ice is H2O. When ice melts and forms water, it's still H2O. So there are no new bonds formed. The hydrogens are still bonded to the oxygen. And that kind of goes together with the no new substance is created. So we had H2O at the beginning. We still have H2O at the end. So some clues to determine that it is a physical change as opposed to a chemical change are there is a change in size, there's a change in shape, there is a phase change, which means it changes from solid liquid to a gas. Phase changes are probably the most common physical changes. So melting, boiling, subliming, that kind of thing. Those are always going to be physical changes because you're just taking one thing and changing it from a solid to a liquid or liquid to a gas or whatever. You're not changing the actual chemical composition of the thing. So if there's a change in length or mass or volume, those are also generally physical changes. So like if we take a piece of paper and we cut it in half, okay, we still have paper. There's no new stuff formed. We change the length and the mass and the volume, but that's still a physical change. Okay. Okay. All right. Now, the way chemical bonding works. First off, chemical bonding changes the properties of the elements or atoms associated with the bonding process. So, for example, we probably mostly have heard that table salt is sodium chloride. Okay. This is the formula for sodium chloride right here, NaCl. It's made of 2 elements. Na is sodium, Cl is chlorine, right? So you guys all know the properties of salt. It tastes salty, obviously. You put it on food, you eat it. It's part of a most people's diets kind of thing. Too much of it is not great, but you can eat it, right? It tastes good. It makes other foods taste good, and you can definitely eat it. Now, compare that to the separate elements, okay? Here we have sodium. Sodium by itself is a super soft metal that, when exposed to water, starts on fire, okay? And chlorine is a yellow gas that is poisonous when inhaled. So just kind of think about that for a second. We have this metal that basically explodes when you put it in water, and you have this gas that if you inhale, you could die. But then when you put those two things together, you get table salt, which all of us eat every day. Isn't that crazy? Like, that's just mind blowing to me that you could take two things that are potentially deadly, put them together, and you get table salt. That's kind of the magic of chemistry, right? So the point I'm trying to make is the bonding process completely changes the properties of chemical substances. Okay, we have two deadly things that, when put together, makes a very much not deadly thing. Okay, so chemical changes completely change the properties of the things that they are involved with. Now, the reason that atoms form bonds is to be unreactive or stable. Okay, atoms want to be stable, and if you remember from the last lecture, atoms that are stable mean they have 8 valence electrons, or a full 8 valence shell. So that is why atom or bonds are formed, okay, to make them have that full 8 valence electrons. Now, there are two types of bonds. There are ionic bonds and there are covalent bonds. We're going to talk about each one of those. So ionic bonds are formed when electrons are transferred from one atom to another atom. So one of the atoms loses electrons, one or more electrons, and the other atom gains one or more electrons. So, for example, sodium has 1 valence electron. Okay, so it wants 8 valence electrons. So again, from the last video lecture, if you have 1 valence electron, you're going to want to get rid of it to drop down to the lower energy level, or the lower valence shell. So it's going to get rid of that 1 electron. Okay, so since it gets rid of 1 electron, it's getting rid of a negative charge, and its amount of protons stay the same. So it's going to become a +1 ion, also known as a cation. Okay, because it gets rid of 1 electron. Electrons are negative, so it gets rid of 1 negative charge, so it becomes positive. Okay. Now, chlorine has 7 valence electrons, and again, it wants 8, right? So it's going to gain 1 electron. Okay, so when it gains 1 electron, since electrons are negative, it's going to become negative. Okay, it's going to become -1 specifically. So once both of those things happen, once an Na becomes +1 and Cl becomes -1, they are going to have one's going to be negative, one's going to be positive, and as we hopefully know, opposites attract. So the positive Na is going to be attracted to the negative Cl through their polarities and opposite charges, and so that attraction between the positive and negative charge is what forms the ionic bond, what makes the ionic bond happen, because they are attracted to each other. So very important, anytime we have an ionic compound that is formed with ionic bonds, the overall charge of the compound is 0. Okay, because again, remember, Na is +1, Cl is -1. When you take a +1 and add it to a -1, they balance out to be 0. Okay, so that works the same way with any charges. So like if we have a +2, then we have to have a -2 to balance it out. Now those charges don't necessarily have to come from just one thing. Let's say we have a +2 ion and 2 -1 ions. Okay, they can bond together. So like if we had calcium, calcium's +2. And if calcium went to bond with Cl, it would bond with 2 Cls because Cl is -1. So if we had 2 Cls, we'd have a total negative charge of -2. So those 2 negative charges would then be able to bond to calcium's +2 charge. Now, ionic bonds generally tend to form between metals and nonmetals. And if, again, you remember from the previous lecture, metals are on the lower left section. Lower left section of the periodic table. Nonmetals are on the upper right section. Metals are to the left of the staircase. Nonmetals are to the right of the staircase. All right, so last thing we're going to talk about is polyatomic ions. Now, polyatomic ions, as you can see from this chart over here, these are just ions that are made up from more than one atom. Okay, so for example, we can look at OH minus, that's hydroxide. Hydroxide is made of O and H, and it has a -1 on it. Okay, now that -1 is very important. If it was just OH, which doesn't actually exist, but pretend, if it was just OH and it did not have a negative charge on it, it would not be a polyatomic ion. It would just be a compound. Okay, in order for it to be a polyatomic ion, it has to have a charge. Okay, and as you would notice, all of these substances have 2 or more atoms and a charge. Okay, and the vast majority of them are negative. The only ones that aren't are ammonium and hydronium. Okay, there are others that exist, but the only ones that you guys need to worry about are ammonium and hydronium. All the other ones are negative.